Hello and welcome to Empowered Learning. This particular video is the next video in the exponential function series. And so what we're going to do now is kind of move up a bit and speak about solving basic exponential equations. If you've watched my video series, you'll notice that the first part of this was just about going through exponential functions and graphing them. So now that we have sort of an intuitive understanding of what the graphs look like, we can also get into the actual equation solving of exponential functions now. So the one thing that we want to remember whenever we're solving equations of any type is that an equation is just another way of asking a question about a graph of a function without actually having the graph in front of you. Okay, so whenever we go and solve what we call simple or basic exponential equations, we have a few properties that we need to remember before we actually start this process. The first one here is this one. And so this basic rule here basically says that if we have two exponential expressions that are equal to each other, hence the exponential equation, then if the bases are the same on both expressions on either side of the equation, then that means that the exponents must be the same as well. Okay. Now, if we reverse the process, then we see that if we have two expressions, no matter what it is, if they're equal to one another, then we can form an equivalent exponential expression by using a common base and letting the things that are equal to each other be the exponents of that particular equation. Okay? And so using this along with what we know about our exponential rules, we can solve some basic exponential equations with ease. If you're unfamiliar about the exponential rules, please check out my videos that deal with the exponential rules as well as the ones that deal with radical equations, radical expressions, etc. Okay? All right, so I have some examples here of some basic exponential equations that we'll use, and then after we go through these examples, we'll do some on our own here. So example A, we have 5 raised to the x minus 2, which is equal to 125. And so here we see that we have on this side of the equation, we have 5 raised to some power. So in thinking about the rules that we just got through looking at, we want to know, all right, is there some way for me to rewrite 125 as 5 raised to a power? Because if it is, then I have a situation like this, where I have 5 raised to some power equals 5 raised to another power. So that must mean that my exponents must be equal. And so it turns out that 125 is the same as 5 raised to the power of 3. So because of that, because of my exponential rules, I know that the two exponents are equal. So I can come here and say therefore, that's what these dots here mean. Therefore, the exponents must be equal, and then just solve for x. And you see I simply get 5 there. Okay. So in example B, we see the same thing. So we see 10 raised to some power equals 10 raised to another power. So the exponents must be equal. And so from here, we start and we state this, and then we notice that we have a quadratic equation because the highest exponent on any variable is a 2. So then from that point, we know with quadratic equations that we move everything to one side, set it equal to 0, and then we can either factor, do completing the square, or use quadratic formula to figure out the solutions to the quadratic equation. In this case, it's a pretty simple one, so we just factor. And so we know that the factors of 7 that add or subtract to be 6 is just 7 and 1. So we factor, and then from that point use the zero product property to set each factor equal to 0 and then solve for x. Okay. For example C, we see that we have two things that are equal to 0. Okay. And so in the first case, we have a linear factor equaling 0, or we have an exponential factor equaling 0. For the linear factor, of course, we just solve it like a linear equation, add 5 to both sides, and then divide by 2, and we see we get 5 halves as an answer. However, for the exponential equation that we have here, we notice that there's no solution for it, okay? And the reason being is that e raised to the x, and just to be clear here, e is an irrational number that is approximately equal to 2.71. E to the x is a function that basically looks like this. And if you remember, one of the things that we said is that we had this horizontal asymptote here at y equals 0, okay? So we know this function cannot cross or touch the x-axis at any time. Well, this equation here is trying to communicate to us, for the graph of the function e to the x, if you have a point that has a y value of 0, tell me what the corresponding x value is, okay? And so we know that this particular function, it can't have a y value of 0 because it can't touch the x-axis. So therefore, it's impossible to have a corresponding x-coordinate for that. So that's why we have no solution here. All right, so moving on to example D, we see that we have the case where 6x e raised to the negative x minus 2x squared e raised to the negative x equals 0. And so we see that we have a common factor of e to the negative x in both terms, so we factor that out, okay? From this point, we know that we have two things that multiply to be 0, namely the e to the negative x and all this here. So we use the zero product property to set each of them to 0, okay? Of course, for e to the negative x equaling 0, I'm trying to work it out algebraically to show you that we have no solution. But really, e to the negative x is a exponentially decreasing function that looks like this, and it cannot cross or touch the x-axis here, okay? And so just like in example C, this is asking, hey, if this function has a point where its y-coordinate is 0, what is its x-coordinate? We know that that's impossible. So here we know for at least this first part here, there's no solution. For second part, we realize this is a quadratic equation. We have a common factor in both terms of 2x, so we factor that out. And so from here, of course, we see that we can use the zero product property again to set 2x equal to 0 or 3 minus x equal to 0. And then from that point, we just solve both equations for x. And so x is equal to 0 and 3 are our actual solutions. For example, E, we see that we have a situation where we're going to have to use our exponential rules to be able to simplify this, okay? We see that we have exponential expressions in this particular equation that are e raised to some power. So our goal here is to say, all right, well, is there some way I can say e raised to one power equals e raised to another power? Because if I can, then I can just say the two exponents are equal to one another. Well, if you notice here on the right side of this particular equation, we have e raised to the 8x times 1 over e raised to the 15. And so we know from our exponential rules here that anything raised to a negative power is the same thing as 1 over that same thing raised to a positive power. If we take the 1 over e to the 15, which is written in this form, and translate it as a negative exponent, we have e raised to the negative 15. Okay? So from that point, the other thing that we realize is that here we have a situation where we have some exponential expression with one exponent being multiplied by an exponential expression with another exponent. And of course, in this case, we know that we can add exponents. If we add 8x and a negative 15, that adds to be 8x minus 15. Okay, so now we have our situation here where we have e raised to some power equals e raised to another power. And thus, from that, we see that the exponents have to be equal. And so now once we get to this point, we realize it's a quadratic equation. So we move everything to one side, set it equal to 0. And so we do that by subtracting 8x from both sides and adding 15 to both sides. And then from here, of course, we have several different ways we can solve a quadratic equation, but it's easiest to factor here. So we factor into x minus 5, x minus 3 equals 0. And then we solve using the zero product property. We set each of those factors equal to 0 and solve for x. And we see that x is equal to 5 and x is equal to 3. All right, so for our last example on this page, we see we have a situation now where the exponents are equal, but the bases are not, okay? And so this particular situation goes along with the second rule that we saw at the beginning of this video, which says that, hey, if we have two things that are equal, then this implies that if we use the same base, that this equation here would also be equal. So in using that, what we realize here that, hey, if our exponents are equal and we have these two things equal to each other, then the bases must be equal. And so in that case, if we set the bases equal to one another and solve that particular linear equation for x, we see that we end up getting x is equal to 3. Okay. All right, so now we're going to go ahead and move on and try some fresh examples. And so it'll be similar to the ones that we've seen here. And I want to do this just to kind of give you an idea, or get you comfortable with it, I should say. All right, so we have 2 raised to the x plus 1, which is equal to 32. And so here we want to see, can 32 be written as 2 raised to some power? Well, it turns out that 32 is 2 raised to the power of 5, okay? And so from that, we know that our exponents are equal. And then, of course, if we solve for x here, we see that x is just equal to 4. Okay? So, for example B, we notice here that we have 1 over e raised to the 2. So we can go ahead and rewrite this as e raised to the negative 2. And then from here, we can add the exponents together. And then realize that since bases are equal, then that means exponents must be equal. And then from this point, we will subtract 3x from both sides, as well as add 2 to both sides. That makes all this 0. We end up having x squared minus 3x plus 2. And then from here, we can simply just factor. So we have x minus 1, x minus 2. And so from there, I'm going to make some room over here. What this basically means here is that x minus 1 is equal to 0, or x minus 2 is equal to 0. And of course, if we solve both of these equations, then x would be 1 here and x would be 2 there. So x being 1 or 2 would be our example for our answers for B. All right, so for example C here, we see that the bases are equal. So that means that the exponents must be equal. And so now from here, we notice we have a quadratic equation. So I'm going to subtract 5x from both sides and add x squared to both sides. So if we do that, left side goes to 0. Right side is x squared minus 5x minus 6. And of course, from there, you could probably factor this out too. X plus, x minus, and then here this would be a 6, and that would be a 1. Factors of 6 that multiply, of course, to be 6, but add up to be a negative 5. Negative 6 will want to do that. So from here, that means that x plus 1 is equal to 0, or x minus 6 is equal to 0, which means x equals negative 1 here, x equals 6 there. Okay. For example D, we notice that we have two expressions that are multiplied together to equal 0. So that means either one of those expressions are equal to 0. So we're using the zero product property here. For the first one, we just have a linear factor, so we can just add 3 to both sides here, and we get x is equal to 3. For the next one here, we know that the answer is no solution. And we know that because the graph of e to the negative x looks like this, okay? But we know it cannot cross or touch the x-axis here, okay? Oops, sorry. Yeah, it can't cross or touch the x-axis here, and thus that's essentially what this equation is trying to ask. You know, it's trying to say, does this particular function have an x-intercept? And it can't, because it can't have a point on the x-axis here. So the only solution that we have here is x is equal to 3. Okay. That doesn't look the way I want it to, but we all get the idea. Okay. All right, so moving on. Our next example, we have a 3x e raised to the negative x plus x squared e raised to the negative x equals 0. We see right now that we have a common factor of e to the x that jumps out, so we factor that out. And so now we have two expressions that multiply to be 0, so that means that either one of the expressions had to equal 0. And of course, we know the e to the negative x equals 0 is no solution. And for the second one here, we have a common factor of x, so we factored that out. And so that means here that using the zero product property, that x is equal to 0, or 3 plus x is equal to 0. And of course, this would be one answer. We can subtract 3 from both sides here and get that x is equal to negative 3, and that would be our second answer. Excuse me. All right, so for example F, we see that in this case, we have the exponents being equal. So what that means is that if this is said to be equal, then the bases must be equal, okay? And so from there, we just subtract 2 from both sides, and we see that x is 3. Okay? So these are some examples on basic exponential functions using some of our basic exponential rules. And to review those, if we have an exponential expression equal to another one that has the same base, then that implies that the exponents are equal. And if we have any two expressions equal to one another, we can form an equivalent equation by changing it into an exponential form where the bases are the same. And another way of saying this is that if the exponents are the same, then that means that the bases must be the same as well if we have an equation.